Our example about voltage is just going to focus on practicing the skills that we learned in the first two examples. So I encourage you to try them on your own first and then check with me because the problems are going to be pretty similar to what we've been doing for the past couple parts. So in the UK, electricity is supplied at 240 volts with a frequency of 50 hertz. This energy supply can be modeled with a sine function. And then there's just a visual there. Probably not needed, but you know. So part A here, we want to write an equation for the energy supply in volts over time. And we want to know when are the devices gaining current on the interval from 0 to 1/50th seconds, which basically just means when is the voltage positive. All right, so let's start by constructing our function. I don't think it was very obvious in the prompt, but if it's supplied at 240 volts, it just means that that is like your maximum voltage. So for the sine curve, it's going to reach 240 at a maximum, pass through the midline, which is 0, and then it's going to go down to negative 240. So you probably already figured. Not a good color. Hold on. Let's do this one. All right, so our amplitude is going to be equal to 240 volts. And what else were we given? We were given frequency of 50. And in case you didn't know, hertz is just 1/second. So yeah, it basically just means 50 cycles per second, what we've been talking about with frequency. And to construct our equation, I can write out the general form here. So we have sine of b times t in this case. That is our general form, and we want to use this to help us figure out what goes where. So we have amplitude. Frequency doesn't help much. We really want to get our wave number, which is b. So we're going to do 1/50 to get period. And that's going to equal 2 pi over b, which means that b, if you multiply, well, not multiply, you switch the 1/50 and b. So you get 2 pi divided by 1/50. So then you flip the fraction, and b is going to be equal to 50 times 2 pi, which is 100 pi. Okay, and we don't have a phase shift and we don't have a vertical shift, which means we're done. Well, not quite, we have to write it out, but we're done finding things. And we just have to put it all together. So 240 sine of 100 pi times t. And that's it. No, it isn't. There's a second part. I was thinking, I'm like, am I forgetting something? I am. All right, so we want to know when are the devices gaining current on that interval. Let me go ahead and move this down. I'm going to need a lot of room for this. So we're given a hint here with positive voltage. So it's just saying that our function, which models voltage, needs to be greater than 0. Hey, this looks familiar. Okay, and then as always, we can take out that multiply constant. It's not going to change anything. Let's set the inside equal to x. so that we can make this easier. So sine of x is going to be greater than 0. Again, that happens on the interval between 0 and pi. So let's replace x back with our t expression. And then you would divide everything by 100 pi. And that is going to leave us with t being between 0 and 1 over 100 seconds. Okay, so when are devices gaining current? And as you can probably figure, if you think about the graph of this, so it'll look something like that, right? And then here's our amplitude of 240. So when t is between 0 and 1 over 100, that is like the first positive segment of the graph. And we can figure that we're going to add another 1 over 100 seconds to get that negative half. If we do 1 over 100 plus 1 over 100, we get 1 over 50. And that was the interval we were given. So this is going to be our interval for positive voltage. All right, let's go ahead and move on to part B. I can move my handwriting in this. It's very cool. So we want to alter the energy supply equation so that the electrical devices receive maximum voltage instantly. So I don't tell you what to change it to, but we want maximum instantly. So at t equals 0, we want 240 volts. And if we look back at our rough sketch of a sine curve, we get 240 a little bit later, and we want to shift it over to the y-axis. So it's looking like we have to change the sine into a cosine function. And let's think about what point, what t value initially gives us that 240. It's going to be halfway between 0 and 1 over 100. So 1 over, let me scroll down, 1 over 100 divided by 2. That's going to be the same as 1 over 200. Okay, and then so if we change this to a cosine function, we just need to make sure we shift it right so that it looks like a sine function. So let's rewrite this as y equals 240 cosine of 100 pi. And then be mindful of those parentheses because they'll get you. We're going to do t minus 1 over 200. So that's our phase shift. Could I distribute this? Yes, but I think it's better to write it this way. Okie doke. So part C is probably the hardest part of this question, but I don't think it's any worse than the graph we did in the last question, so hopefully that's reassuring. Let me start by creating a little graph here. So we want to change the previous equation into, okay, that says inverse. No, that's not correct terminology, I'm sorry. It should say reciprocal. So we want to change it to its reciprocal trig function, which is different. So in the last part, we had a cosine equation. The reciprocal of cosine is going to be secant. So we're doing 240 secant of 100 pi and then everything else stays the same. Okay, so what I would do in this situation is first we got to figure out kind of our scaling. That's always the thing you want to do first. And this 0.04 looks oddly specific. It probably means something. And as a fraction, it is 2 over 50. And our period, we know is, our period is 1 over 50. So this is 2 cycles. And then I like to do my point of interest kind of thing. So remember, it still looks like a sine function. So we're still writing it this way. So that's 2 cycles. So we have 1, 2, 3, 4 points of interest. And then we're going to see our interval right here. We're going to do 2 over 50 divided by 4, which equals 1 over 100. So again, that is our step. And we're going to make 4 points here. So 1, 2, 3, 4. This will be 1 over 100, 1 over 50, 3 over 100, and 2 over 50. Let's also put our amplitude here, 240, negative 240. Okay, first thing we might want to do is graph the easier function, which would be the cosine. So, and I'm just going to write cosine because, again, don't let that phase shift stuff scare you because it looks identical to the original graph. It's just written differently. So let's just kind of write it like a regular old sine graph. Well, a regular old sine graph doesn't look this weird, but doing my best. Okay. And then the second graph is going to be our secant. So, all right, secant. That's weird. My marker is being weird. Okay, and this is going to be really similar to the process that we used in the last example. Why is it dotted? Okay. All right, you know, we're gonna be dotted this time. We're gonna be dotted. So it's so weird. So we know that secant is just 1 over cosine, so we're going to do 1 over these values. The peaks are going to stay the same. Anywhere that our function equals 0, we're going to have asymptotes. So all of these points kind of looks like raindrops in this font. Okay, I think I fixed it. It was kind of getting on my nerves, so. All right, good. Good, good. So let's go ahead and put our points on the peaks. And we already know that our graph is going to do this. Again, I'm going to get more into that in the next example. But remember, it just kind of moves outward from the peak. And that is the graph of our function.